Hello everybody, this is Cal with sections 14.3 partial derivatives and 14.4 tangent planes and linear approximations. These are two kind of long sections, but we're going to try to kill them in one video. And I will say they're long, but they're not terribly hard, and your book is way wordier than it has to be for these sections. Your book starts out section 14.3, partial derivatives, with a motivational example about the heat index, which is a two-variable function based on the temperature and the humidity, and it returns you what the temperature feels like. Do read through this example, but honestly, your book kind of treats this a little bit more difficulty than it has to. The takeaway from this example, and the takeaway in general from the definition of partial derivatives, is that a partial derivative of a function of x and y, let's say, with respect to x, is the derivative where you treat y like a constant and you vary x. You want to hold one variable constant and take the derivative with respect to the other. You're asking, how does the function change when I vary only one variable? And we can see this on page 927. We have a rule for finding partial derivatives of f of x and y. To find the partial derivative of f with respect to x, regard y as a constant, differentiate f of x and y with respect to x. To find fy, regard x as a constant, differentiate f of x and y with respect to y. With that in mind, it might be a little bit easier to understand the motivating example on page 925 with the heat index. Now, I mean, your book, of course, is a good little math book, and it goes through and, defines this in terms of the limit definition. But I'm going to assume at this stage of your life that you kind of know how the limit definition of a derivative works. And we're going to kind of assume that it works the way we expect it would, and move on with our lives. I do want you to pay attention to the notations for partial derivatives on page 927. In particular, these are not d's, they're little curly d-ish things in partial derivatives. We use d's for full derivatives, and these little curly, we call them del's usually, little curly del's for partial derivatives. Do go through example 1, make sure you understand what's going on here. You are going to need to find a lot of partial derivatives, and so hopefully this is something you can deal with. I also really like this section on interpretations of partial derivatives. I would read this very carefully and make sure you know what they're saying. And there's some really good figures for this on page 928, figures 2, 3, and 4. I'll give a really good idea of what the partial derivatives mean. Example 2 is also a really good example, so make sure that you read that thoroughly and understand it. Example 3 is another example of calculating partial derivatives, and this is a good one. Make sure you understand what's going on. And example 4 is an example of partial derivatives using implicit differentiation. Also pretty key. Make sure you remember what implicit differentiation is and how this works. There's a discussion here of functions of more than two variables. Again, your book develops this using the limit definition of the derivative. You can kind of gloss over that. I more care that you know how to find partial derivatives. So look at example 5. The section on higher derivatives is also pretty important, including especially the notations. Be really careful with notations on the order of operations with higher order partial derivatives. Make sure you understand what these notations mean pretty carefully. So the center of page 930 is pretty important. Example 6 is a great example. You should work through it. And you'll notice as you find the second order partial derivatives of the function here that the mixed partials, fxy and fyx, end up being the same. This is not a mistake. There's actually a theorem about it. It says, more or less, that if your mixed partials are both continuous, they'll be the same. And this kind of works for higher order derivatives as well. So read page 931 relatively carefully, and example 7 is good as well. I would say in example 7, try computing some of the other mixed partials and see what you get. Just play around with this concept. We're not really going to pay attention to the section on partial differential equations, so you can basically skip that, although it may be of interest to some of the physicists in the audience, especially, and some of the engineers and so on. I'm not going to say that this is valueless. We're just not going to spend time on it in our class. The Cobb-Douglas production function is another example. This is going to be really good for the economists in the audience. But again, we're not going to spend time on it in class. So that ties up section 14.3. A lot of homework problems in this section, and I recommend that you spend a lot of time practicing partial derivatives, second order partial derivatives, higher order partial derivatives, and so on. Just get really, really used to taking partial derivatives. We'll move straight on to section 14.4, tangent planes and linear approximations. Tangent plane is like a tangent line. I think you have a pretty good mental image of what it should be. And the beginning of this section kind of goes through finding a formula for a tangent plane. We'll go over that in class, given enough time. I want you to know the formula. It's not a hard formula to find, actually. But we'll go over that in class. You definitely should, however, be able to find an equation for a tangent plane to a surface at a point. Part of the beginning of this section, by the way, is your book reminding you how the equation of a plane works, and hopefully you still remember that from 12.5. Example 1 shows a good example of finding an equation for a tangent plane, and this is definitely something that you all need to be able to do. On 941, we talk about linear approximations, and a linear approximation is an equation of a tangent plane where we've replaced the z by a function, L of x and y. It's when you plug in x's and y's to approximate values of your function by using the tangent plane. If you remember linear approximations in Calc 1, this is the same exact thing. And you might want to refresh yourself on linear approximations from Calc 1 if this is unfamiliar. Do read page 941 pretty carefully. It reminds you of some language and some motivating examples. On page 942, your book goes into a discussion of differentiability, and I actually don't like this discussion very much. It's not very intuitive. It probably will not look that familiar from Calc 1, and so I would say skip the bulk of page 942, like from the second paragraph, probably down through definition 7 and a little bit right after it. You can kind of take theorem 8 as your definition of differentiability. If your partial derivatives exist and are continuous at A and B, at a point A, B, then f is differentiable at A and B. Differentiability is all about partial derivatives. Example 2 is a good example. You show that a function is differentiable at a point and use the differentiability to approximate it near that point. I like example 2. And example 3 goes back to that motivating example of the heat index from the last section and does a linear approximation using this example. We will also talk about differentials in class, and differentials are basically a different language for a tangent plane. That's actually a pretty important sentence I said. I'm going to say it again. Differentials are basically a notational shift in the way we deal with the tangent plane. You should be able to deal with this concept using differentials or using linear approximations or using tangent planes. They are all the same thing. You do need to know the formula for a differential. You need to be able to use a differential. And so I recommend that you pay close attention to example 4 and example 5. Your book then talks about functions of 3 or more variables. There is really no difference between what's going on here and what was going on with 2 variables. Example 6 is a really great example, and you should pay close attention. And that ties together these 2 sections.